Hi to all. How are you students? Welcome to Srinivas physics classes. Today's topic, continuation of applications of ampere circuital law. Previously we discussed about the ampere circuital law and its application. One application we discussed. Second application I am going to start, that is for solenoid. Our topic is solenoid. This is the second application of ampere circuital law. Right? By applying the ampere circuital law, I am going to derive the magnetic induction on the axis of the solenoid. Okay? Listen very carefully. And now the topic is magnetic field or induction on the axis of long solenoid. What is a solenoid and what is its use? Solenoid is an insulated wire. Okay, insulated wire. The copper wire, it is insulated, right? That means the plastic insulation is there over the wire. That is insulated wire, okay, wound on a cylinder is called as solenoid. Okay, then look at here. This is a cylinder. Okay, look at here. This is a cylinder. On this cylinder, we are wounding one wire, right? And now this is called as solenoid, and some current passes through this solenoid wire. At that moment, the magnetic field produces and it can act as magnet. And now if we draw the magnetic field pattern produced by the solenoid, then it will be like this. It acts just like magnet. Look at here how the field lines will be there, and for that we draw this diagram in different way, and this is the block lines, this is the solenoid, and here the current is coming out. Okay, current is coming out and this will be enter into the down. This current coming out can be represented with dot I. Okay, this is the dot I. Okay, circle with dot. This is the current coming out. The current is coming out and then enters into this. Right, here it is coming out, the current is coming out, here it is entering, it is like coming like this, and then after that here it is entering. Okay, at the down we are writing the cross means entering. Here at the top line we are drawing the dots, that means they are leaving from the board. Okay, like this, coming outward and entering into the board. Okay, perpendicular to that one. Now let us see how the field lines will be there. When the current comes outward, according to the right hand thumb rule, the field lines like this will be there, right? Anti-clockwise, like this. And here the cross mark, cross means inward, current is inward. Thumb shows the direction of the current and curled fingers indicates the field. Then look at here, inward. Okay, this is inward. Inward means field lines like this. That means the clockwise. Then we are drawing the clockwise at the down. Okay, and here when we draw like this, here we are seeing this is right side, right side, right side, right side, right side. Here also right side. That means inside the solenoid we are getting the field lines right side. That means the magnetic field is also right side. That means the magnetic field inside the solenoid is towards right side. And now these lines, okay, are very close and all are parallel to each other inside the solenoid. That means the magnetic field is strong, okay, and it is uniform. Okay, field lines are parallel means they are uniform. Okay, magnetic field strength is constant. And let us see the capital L length. L is the total length of the solenoid, and number of turns. Look at here, this is the one turn, 2, 3, 4, 5, like that. There are considered as n turns are there in the solenoid. Okay, L is the length of the solenoid, and capital N is the total number of turns in the solenoid, and small n is the number of turns per unit length, N by L. I is the current in the solenoid, and here inside the solenoid the field is maximum. Okay, this field I am going to derive inside the solenoid field. I am going to calculate. Okay, then for that, look at here, I am drawn this diagram, redrawn this diagram, and I will apply the ampere circuital law to find the magnetic field. Let us see. This is solenoid. Here dots indicates the current coming outward like this, and here the current is entering. Okay, and now this is the meaning of this one dot. It's a solenoid. Here the current is leaving it here and the current is entering it here. Now look at here, this is like this, the wire is there, the current is like this, here the current is coming out and here the current is entering. Okay, leaving we write dot and entering we write cross. Look at here, in order to find the field on the axis, what is the direction of the field on the axis? Okay, now current is like this circle, right? We take the curled finger size current and the thumb indicates the field, like field is on right side. Okay, like this, field is right side. Now here I took the one loop in order to find the magnetic induction. Okay, that loop is PQRS is the loop to find the magnetic field on the axis of solenoid. Look at here, at PQ, according to ampere circuital law, what we know, integration of P bar dot dl bar is equal to nu naught times of enclosed current. Then this PQRS is the closed. In this closed loop, what is the enclosed current we have to write, and integration B bar dot dl bar about this loop we have to find out. And this I am splitting this loop, and that means this loop is PQRS. I am splitting P2Q. Okay, P2Q, next Q2R, Q2R, R2S, S2P. Then this integration B bar dot dl bar is integration over the loop, but the loop has 4 parts, P2Q, Q2R, R2S, S2P. This I am splitting. Okay, this is the according to amperes circuital law till now. And now let us continuation. What is that? The continuation is that from P to Q. Okay, P to Q, P to Q. Okay, look at here, P to Q, PQ part. For PQ part, B bar, DL bar, how they are there? DL is a small element I am taking right side, and B also right side. That means B bar parallel to DL bar. That means angle between the B and DL is 0. Then what happens to the B bar dot DL bar? B bar dot DL bar is BDL cos theta. Theta is 0. Then we will get as BDL, right? Similarly, and for other parts also we can find out the B bar dot dl bar. B bar dot dl bar is there. For every part we have to find out. Okay, now you take the screenshot of this. Okay, it was very easy, and it is this solenoid used to produce the magnetic field. It is used in the radio or television like that. Okay, and listen very carefully. Now I am going to continue. For the PQ part I calculated the B bar dot dl bar. Similarly, RS part also, QR part, RS part, SP part, for every part I have to find out the B bar dot dl bar. Okay, then after that I will substitute in this, then I will get the final answer for the B. Okay, listen very carefully, and then I will rub this, and then after that I will continue it here, and you take the screenshot and note it, and this is very important. Okay, look at here. Now I am going to derive the magnetic induction. For the PQ part we derived. Next I will take the QR and SP. Okay, for the QR and SP part, for QR, PQ completed, then QR part we will take. For QR part, then what happens? For QR part, you see the B bar perpendicular to DL bar. B bar right side will be there. Okay, DL bar is like this there. That means DL and B. DL is a small part on QR, that is downward. Right, B right side, B bar perpendicular to DL bar, then theta 90 we will get. Then what about the B bar dot DL bar? What you will get? B bar dot DL bar we will get as, right, what you will get, tell me? BDL cos theta. BDL cos theta means theta is 90, then it will become 0. BDL cos 90, it is 0. Then for other part I will take. For RS, PQ completed, QR completed, RS. For RS part, okay, for RS part, what happens? B bar perpendicular to, not B bar perpendicular to D bar. Here B is 0 nearly. It is outside of the solenoid, the B value is nearly 0. Okay, it is very small. Then we write B bar dot DL bar as again 0. Then next part is for PQ completed here. Okay, RS completed. Next SP complete. SP is the last one. Okay, for SP part. For SP part, what happens? B is again right side, DL is perpendicular, right? DL is a small element on SP. Then B bar perpendicular to DL bar. Then what you will get? Theta is again 90 degree. Then we will get B bar dot DL bar as BDL cos 90. Theta is 90 here. Then again 0. Right, this all we substitute in above equation. And enclosed current also I want. Okay, enclosed current. Okay, now enclosed current in this loop. In this loop, how much current is there? For example, in this loop, capital N turns are there. Okay, N turns in the loop. If capital N turns are there in the loop, present in a loop. Okay, if capital N turns are present in the loop, then enclosed current, what happens? Enclosed current in the loop. Enclosed current will become like this, right? For one turn, how much current present? I current. For N turns, how much current present? Ni, right? In each turn, I current passes. There are N turns are there. Here current is entering, here current is entering, here current is entering. Right? Like that. N turns. Ni we write. Then this all we substitute in this equation. Okay? And now, when we substitute this all in this equation, then what you will get? Integration. This is equation 1, let us take. And from equation 1, we write. From equation 1. What do we write? Integration P2Q, we write as B bar dot DL bar is P2Q is BDL, right? Plus, what about the Q2R? B bar dot DL bar is 0. Then this part is 0, this part is 0, this part is 0. That means plus 0 plus 0 plus 0 is equal nu naught times of enclosed current is what? Ni. Okay, right side. Enclosed current is I, enclosed is Ni. Then we write B is outside, then B integration DL P2Q, that is nu naught Ni. Okay, integration DL is what? DL is a small element on the PQ. DL is a small element on PQ. Then integration DL. Integration DL is the full length of the PQ. Full length I will take capital L. Okay. Length of PQ. Then what you will get? B into L is equal to mu naught Ni, right? Then B is equal to I want mu naught Ni by L. This number of turns per unit length we can take as a small n. Then B is equal, we will get as mu naught small Ni also, right? This is equation 2. And B is equal, we can also write as B mu naught small Ni. Why? Because we know that number of turns per unit length is said to be small n. Okay, right? This is the derivation. It was very simple. And note it. Take the screenshot and note it. Okay. Okay, let us go for the third application, that is the magnetic field due to toroid. Previously we discussed the solenoid, now toroid. What is a toroid? If the solenoid is bent in the shape of ring, then it is called as toroid. Already we know solenoid, this one. If it is bent in the shape of circle, then that is called as toroid. This is solenoid. You can bend in the shape of circle or the ring, then that is called as toroid. Toroid also used to produce the magnetic field. Now magnetic field formula I am going to derive for the toroid, and let us see. The inner radius of the toroid is r1 and the outer radius is r2. The average radius, okay, look at here, up to the axis, right? This is considered as the axis, and up to the axis the radius we can take as r, and this r we will get as r1 plus r2 by 2. I is the current in the solenoid, I is the current in the toroid, okay, number of turns are there. I is the current, r1 is the inner radius, r2 is the outer radius, r is the average radius, okay. Capital N is the total number of turns in the toroid. I am going to derive the first b on the axis of the toroid. This is the axis of the toroid. At this point I want to find out the b, and this distance, red color circle radius is smaller, red color circle radius is smaller, okay. And this we are taking some loop, and the loop small element is dl, and b I am going to derive on this axis at point p. This is p, this element length, this is dl, and this radius is smaller, b I am going to find out, okay. Listen very carefully. Now it was very simple. According to ampere circuital law, what we know? Ampere's circuital law. Do you know ampere circuital law? Yes, you know very well, right? That is, according to ampere circuital law, we write line integral of p bar dot dl bar is equal to mu naught times of enclosed current, okay. And then what is the line integral? Let us go for the line integral, okay. Line integral of around this closed path I am going to find out, and b and dl are parallel to each other. Then we write here like this. Let us continue. I am going to give the derivation. B formula I am going to derive. Okay, on axis b bar parallel to dl bar, then we write theta is 0. Then what you will get the b bar dot dl bar? B bar dot dl bar you will get as b dl cos theta. Theta is 0. Then cos 0 is 1. Then we will get as b dl, right? Cos 0 is 1. Then b dl we will get. Let us see. And this we substitute. What is the enclosed current? Enclosed current in the loop, right? Enclosed current. Then enclosed current we can find like this, okay. Look at here, this is the closed loop. Here the current is entering, that's why here cross, here current is leaving like this dot. These dots are there. In each dot I current is leaving here. Then around this red line, inside the red line, okay, this is the closed loop is the red line, okay, red circle. Inside that there are some turns are there, n turns. In each turn I current flows. Then total current flows, that is inside the red circle is Ni, right? How much? Ni. This all we substitute in this equation, then we will get simply B formula, right? Let us go for that. Integration b bar dot dl bar is bdl is equal to mu naught enclosed current is N. Okay, let us continue now. That is integration b bar dot dl bar. B we write outside. Then b integration dl is equal to, we will get as mu naught ni. Then integration dl is what? Integration dl is L, total length. Total length is this red line circle length, that is capital L, but the capital L is 2 pi r, right? Okay, 2 pi r we write. 2 pi r, okay, mu naught ni. Mu naught ni. Because integration dl is the full circle length. We take capital L, that is mu naught, circle length is 2 pi r because it is radius is r. Then we will get b is equal to mu naught ni by 2 pi r, okay. If you take this 2 pi r as L, okay, this 2 pi r is L, then mu naught ni by L we write. This n by L is the number of turns per unit length, we write as small n. Then the B formula we will get is mu naught ni also. This is the formula for B on the axis. The same formula is like as outside on the axis of the solenoid also we got the same formula, right? Okay, I am going to continue. I want to derive the B formula outside and inside. Okay, look at here. This is solenoid already we know. Okay, solenoid, if it is bent in the shape of circle, then we will get as toroid. This is the toroid. This is the toroid. I want to derive the formula for B at here. I will take a circle like this. At this point I want to find out the B. This point I will take as Q. At this point I want to find out the B. Okay, and one more point I will take it here. Okay, this is R. At this point also I want to find out the B. You take this as circle, okay, radius, and you can make a circle at this point, at these 2 points, at here and at here I want to find out the B. Okay, outside and inside. Then how you will get? Now for that, according to Ampere circuital law. Okay, look at here. I am going to find out the magnetic induction inside and outside. Okay, here I want to find out the B. Here I wrote Q symbol and B is equal to question mark. Here I wrote R symbol, right? This point is R. At here also I want to find out the B. The B is equal to question mark. Magnetic induction at here you want to find out. Here already we find out this point I took as the P. At this point we find out the B as at here. Okay, but here I want to find out, here I want to find out. For that, what I have to do, how to find out it? It was very simple to find out. Again we have to use the Ampere circuital law, right? According to Ampere circuital law, what we know, that is line integral of magnetic induction is equal to nu naught times of enclosed current, right? Now, but what is the enclosed current in this? In this closed loop there is no current because the current is here only here. Here the current is leaving and here is entering. This is dot, current leaving, this is crossed. Okay, it is entering. Dot, leaving and entering. That means all the currents are there outside of this loop. Inside the loop current is 0. What about this? In this also current is there. Entering current is there. Leaving current is there. Entering current is there. This is cross, and leaving current is there. That means how much current entering, that much current is leaving. That's why in this total loop, right? Again enclosed current is 0, right? Enclosed current. But enclosed current is 0. But I enclosed is 0, right? That's why integration B bar dot dl bar is equal to 0. Then from this B is equal to 0 we will get that the B is equal to 0 at this point and at this point, but B at point P is nu naught Ni. Okay, this is about toroid. Okay, take the screenshot and note it every point. Okay, it is very important. What is the use of the solenoid and toroid? Solenoid and toroid are useful to produce the magnetic field. Okay, look at here. Let us go for one problem. The solution of this problem. A solenoid of length 0.5 meters. Length of the solenoid is 0.5 meters. Has a radius 1 centimeter. It is very much less. And made up of 500 turns. The number of turns, the total turns is 500. And the current carries is 5 ampere. If you want to find out the number of turns per unit length, N by L is 500 by 0.5, right? 5 0.1s and 5 hundreds, right? And now we will get the 1000 turns per meter, right? Turns per meter. Then what they are asking, magnetic induction inside the solenoid. Formula is nu naught Ni. We substitute all values in this. Nu naught is 4.10 power minus 7. Small n is 1000. Right, I value how much current flows in this 5 ampere, right? It was very simple. Okay, and then we will get 4 into 5, 20 pi into Okay, 4 into 520 pi into 10 power minus 7 10 power 3, this one 10 power minus 4 we will get, right? And this we will get as 220 into pi value is 3.14 into 10 to the power of minus 4, then we will get as this is 62.8 into 10 to the power of minus 4, or the 6.28 into 10 to the power of minus 3 Tesla. That this is the answer. And I am giving one homework similar problem. Solenoid coil of 300 turns per meter, number of turns per unit length they gave, current they gave, length of the solenoid is 0.5 meter and the radius is 1 centimeter. Then they are asking to find out the magnetic field inside the solenoid. Okay, then same formula you can use and you can solve it. Okay, and thank you for watching my lectures. Subscribe my channel, share to your friends.